Good morning, this is your Stat Sensei, Mr. Spensei, and this is a warm-up on the paired t-test. Please remember paired data is data that's been tested twice in some form or fashion, whether it's someone got specifically tested twice or twins got tested twice. And the reason we do that is to control for outside variables. Paired testing is probably the most powerful testing that we do in statistics and intro statistics, but it's not always available to it. That's why we can't always do it. Sometimes we can't test twice. So a high school wanted to know whether a new reading program would result in a higher reading scores. 10 students were randomly selected from a school of over 1,000. So we know that our number of students, our sample size is 10, so N is 10. And that's given to us right here from a sample school of over 1,000. So there's our population size. Before program test scores and after test scores are listed. So they were tested twice. They were tested before they took the program and then after the program. At the 1% alpha level, or level of significance, so they're telling us our alpha is 0.01. Is there evidence that reading scores improved? In other words, did they go up? So improved tells me that the after score should be higher than the before scores. So before, after. So before should be less than after. That's what they're telling me should happen. All right. So they're wanting us to run a hypothesis test, obviously, because they're asking us for a level of significance and they want us to test, and they're looking for us to gather evidence. The word evidence also tells me that. Well, my formula is essentially the same as a t-test. In this case, it's going to be t equals x bar d minus mu d sd divided by the square root of n. The d stands for the differences because I'm going to have to subtract this value. So because essentially I have t equals x bar minus mu s divided by square root of n. That's a regular t-test, but we're running a paired. So we're going to have to subtract to find these differences here. Now I could subtract these out by hand, or I could have the calculator do it for me automatically. Well, I've already input the data into the calculator. So I've input the before program scores in L1, the after program scores in L2, and I'm going to have the calculator calculate those differences. And here's the way we're going to do that. We'll press the blue button or to get L1 minus the blue button L2, blue button 2 to get L2. And there we are. We did the differences. 70 minus 78 gives us a negative 8, et cetera, et cetera. All right, so I did all the subtraction. The fact that it's negative would indicate that the before scores are lower than the after scores. That's why they're negative, because it's basically saying, hey, if we had a 60 here and then it went to a 70, 60 minus 70 is negative 10 because the before score was lower than the after score. All right, so now that I have that information in a calculator, I can go stat calc, one variable statistics. And the data I'm interested in is not an L1, it's not an L2, it's the differences that I created in L3. So blue 3, all right? And I have a sample mean of -6, a sample standard deviation of 1.414, and we know that we have 10 pairs of data. Please remember the N is the number of pairs. That is the number of pairs. Now, whenever we're running a paired test, we're assuming that there is no difference. We're assuming the program was not effective. If there's no difference, that means, oh, they made a 60 on the first one, they made a 60 on the second one, so that's 0. So that's assuming that there's no difference. So the mean is assumed to be 0. And these values that I have right here is what I calculated on the calculator. X bar being -6 and a sample mean of 1.414, and this N is the number of pairs. We're going to run a one sampled paired t-test. All right, for the mean of the differences, And when we go to draw that, all hypothesis tests are centered on the mean. So in this case, all paired data is going to be centered on 0. We have an X bar of -6. So it's over here. And we said less than, so we're shading off to the left, and this should be a less than here, which means not sure what happened, but this right here is what we're looking for, less than 0. So when I plug in, I have -6 minus 0. It's the x bar of -6 minus the population mean of 0, the assumed, the standard deviation of the differences, and the number of pairs here. All right, continuing on. My null hypothesis is, well, that there is no difference. And remember, all null hypotheses are written as equal. So mu d equals 0. Super important that you include that d. All will be 0, and all paired will be 0 here. All right, the alternative. Well, we said less than, that's what we have. So everything's going to match, but our inequality is going to change to a less than because we said, hey, you know what? Before they scored a 60, later they scored a 70. So 60 is less than 70. That's how that order went. Let's go ahead and run this test. Stat test, just running a standard t-test. We have data, so we need to make sure data is highlighted. The mean of the population is 0. And the data we're interested in is not in L1, it's not in L2, it's that difference is in L3, so blue 3, and we need a little less than. So be really careful. We got a really big t statistic of -13. Be careful about this. You'll never have probability greater than 1. So if you think you do, you better look for that E. So here's what we have. The probability that t is less than -13.4164, and we have 1.4804 e to the -7, which means I need to go 1, 2, 3, 4, 5, 6, 7 places. I need to move the decimal place 7 places, and whatever that value is, that's how many zeros I'll have in front. So one less than that. If this is 7, then I'll have 6. 1, 2, 3, 4, 5, 6. Well, the rule of thumb is as soon as you get to 4 zeros in a row, we say it's approximately 0. All right? So this is approximately 0. So our p-value is 0, and our alpha was 0.01. Well, 0 is definitely less than 1, so we're going to reject the null. All right? So that's our decision. Going ahead and running a confidence interval for the same thing, it says create a 97% confidence interval. Well, we have x bar plus or minus t star s divided by square root of n. As you can see, the only difference between it and a regular t is we're talking about the differences because we're talking about the data in our column L3 where we subtracted. All right, so let's do that real quickly. Stat calc, 1 var stats, data's in L3, and the average of, you know what, I should look at that, show you that right there. That's what I'm interested in because that's 70 minus 78. So stat calc, 1 var stat, blue button 3 to get L3. And there's my sample mean, etc. And that's the information I need to fill in this next part. Please remember, n is the number of pairs, and our degrees of freedom formula is n minus 1. So 10 pairs minus 1 tells me my my degrees of freedom in this case are 9. All right, our t star, which you can see on the screen already. Second vars, inverse t, 1 minus 0.97 divided by 2, 10 minus 1. And we end up getting 2.5738, and as always, we make it positive. Well, we can go ahead and start plugging in our values into our formula. For our sample mean, we're plugging in -6, plus or minus. Here's our t star. There's our sample standard deviation divided by the square root of the number of pairs, which happen to be 10. All right. So when we draw this, all hypothesis tests are centered on the population mean, but all confidence intervals are centered on x bar because we see x bar in the center there. So we need to be centered on -6 in this case. All right, that -6 came from right here because that's what our X bar is. We're going to have a lower bound and an upper bound, and we're running a one sample paired T interval. So when I go to run this thing, I'm going to run this just like a regular T interval, stat test, drop down to number 8, which is T interval. Data is highlighted. List is an L3. My confidence level is 0.97. And I get a lower bound of -7.15 and -4.84. All right. Now, what that means in this particular case, because remember, we went with before minus after. Well, it means the before points are like 7 points lower to 4.8 points lower. No more. So before you took the program, your score was going to be on average 7 points lower to 4.8 points. So the program seems to improve the scores by 7.4 because the before is 7 points lower than the after or to 4.8 points below. All right. I hope that helped. Look forward to seeing you on the next one. Thank you so much.